Well, thank you. That's actually a very good segue over to Steve. And Steve, as the board shows, is the technical director of the Urban Air Initiative, but has also been closely associated for many years with ICM, which is probably the largest manufacturer of ethanol manufacturing equipment. And so he's intimately familiar with the ethanol production process as well. Steve, we're going to let you do a little technical detail.
Well, thank you, Reed. Your introduction, I thought, was really good of going through the issues here. 8 years ago, we started the Urban Air Initiative, but I think back to about 10 years ago when I was actually doing a large octane study with Ford and John Deere. We actually had an oil industry involved, and they provided some of the test fuels, and I thought it was kind of odd that there was no benzene in their test fuels. And I asked him about it. He said, well, it's against company policy to put known carcinogens in test fuels. Yeah, we could do that to consumer fuels. So that was kind of my first introduction of test fuels, which I'll talk about in a little bit here in a couple of slides. But our focus has been to research the benefits of ethanol, what the refineries do, what the auto industry needs, and especially we are looking at the science here in the EPA models. So as we talk about ethanol or aromatics, it really is a discussion about octane that should be discussed because the aromatics at the oil refinery is what the oil industry goes to when they need to even bump to get to the minimum octane. So I'm going to try to put a face to a name here a little bit in my presentation. In the initial slides is we use the term BTEX a lot, but I'm going to just try to explain this and hopefully don't go too far. But if we look at aromatics, in gasoline, we look at something that's very high carbon intensity to produce, and it also has the highest carbon per energy. And then we're going to be talking about all the health concerns there. If we look at ethanol, we have a low intensity to produce from a carbon point, but we also have less carbon per BTU. It's renewable, and I think the interesting thing is from an octane blending value, ethanol has twice the octane blending value of any component in gasoline. So it's a very effective way of raising octane in our fuel supply. I thought here I should probably try to even introduce what aromatics are a little bit. If you look at any automotive study, they will at least break gasoline down into 3 major groups of hydrocarbons. And so in the bottom picture, I thought, well, it'd be kind of interesting to take the most common component of each one of them and let you see that the aromatics in the middle are the worst for producing soot. They have the most resistance to combustion. So I kind of coined the name the good, the bad, the ugly. 65% of gas is saturates. They're prone to much better emissions, but they don't average as much in the octane category here. So the oil industry is going to primarily rely on that 25% aromatics to raise octane. So I thought I was just going to try to introduce to you to that 25% in the summer months, you know, what aromatics are, but they're really anything built on a benzene ring structure. This double bond in carbon is really the cause of a lot of the incomplete combustion, the formation of the toxics, and so I'm hoping you'll have a little bit better understanding. Any study I reference here has got a link if you wanted a copy.
Steve, could I just interrupt?
Sure.
Because I think you make a very important point, that all aromatics, by definition, have a benzene ring.
Right.
And EPA reacted to the congressional directive by regulating benzene directly, but they didn't do anything about the other compounds with benzene in them.
Right. And actually, my next slide will be a good lead into that. I'm introducing you to the family of aromatics. We can say toluene, but it's still methylbenzene. Every one of these aromatics has benzene in its name. We often say BTEX because those are the most common ones, but over half of aromatics are 40 plus other aromatics, and some of these can be even worse. And so you kind of got a figure here to the right-hand side of this slide, because it's all based on distillation. We go all the way up to even the simplest PAHs in our gasoline. We can say naphthalene, but if it's pure, we would just say mothballs. So But to characterize a little bit more on aromatics, like I said, the refineries produce this. It's higher in carbon. It is the primary source for a lot of the toxics we're going to be talking about. It's slightly lower in the wintertime. Aromatics also has the highest rate of emission. So when we look at the volume in the fuel to what we're measuring on a percentage out the tailpipe, ethanol or aromatics has the highest rate of emission compared to any other component. And then lastly, it's also, which doesn't get a lot of attention, is aromatics is also the biggest concern for material compatibility, especially in small engines. So especially the variation of aromatics. So there's a lot of baggage associated with aromatics before we even get into the emission side of things. I believe there's a good success story when we talk about what happened as we transitioned even to E10. In the green line in this chart shows the ethanol content going up from just a few percent to nearly 10% over a 10-year period. But in the solid red line, you're seeing actual consumer gasoline aromatic content going down. We can see that the refinery has lowered aromatics, and then you get the dilution of adding the ethanol. So even the E0 to E10 has a great success story today by saying we're preventing anywhere from 7 to 8 billion gallons of aromatics being in the market today in the U.S. The U.S. actually averages lower aromatics than Europe, but we have a ways we believe we can go. Lastly, the market survey data over the last couple years has shown that we're starting to go back up in aromatics, and a lot of that has to do to the sulfur reduction that's going on. And the oil industry is actually struggling just to maintain octane in today's market. So the oil industry cannot compete against ethanol from an economic point of view, especially. I think when we go back to why did we start the Urban Air Initiative, I was actually seeing a lot of the health concerns in automotive studies. We have General Motors here talking about toxicity and respiratory disease, these particulate that actually can get right into the bloodstream, causing the damage to the blood vessels. And so we were actually reading this in automotive studies. We have a lot of health studies studying health effects, but how do we tie the reduction of those benefits of health studies right back to the source? But here's just an interesting couple older papers actually we were looking at seeing these concerns. Earlier this morning you heard Reed and Carol talk about SOAs and PAHs and all that. So I kind of wanted to tie this together, why it's all associated to aromatics in our fuel. In the little figures on the right side of the slide, you kind of see the single benzene ring going to the PAHs, going to the UFPs. So any one of these 5 listed here, you can find more health studies focusing on each one of these. So, but they're all tied together. So in the aromatics, the EPA study showed benzene going up with increasing aromatics, even though the benzene in the fuel didn't change from a volume point. But the aromatics then also contribute to the PAHs. So what I'm trying to say here is you can't have PAHs until you have the aromatic structure. And then as we look at the ultrafine particulates, as these PAHs go on to create the ultrafines, we can't have the ultrafine particulates until we have PAH formation. So they're really tied together, feeding each other. And then it's also important that as we get to the UFPs, that's what's coming out the tailpipe. Now we're going to start talking about the secondary organic aerosols, what happens in the next 24 to 48 hours. And EPA recently had a report that showed 50% of MSAT, mobile source air toxics in urban areas, actually comes from SOAs. So there's a huge category. And then some health studies will actually look at PM 2.5, but in urban areas, a majority, over half the PM 2.5 is the SOAs. So you can see how these all kind of tie together back to aromatics in the fuel. I'm going to show a couple slides here just on some of our research showing emission benefits of not only ethanol but some varying aromatics. So even a couple years ago, we took 3 vehicles to an auto manufacturer's test lab near Detroit, and we tested multiple fuels. But here I'm just showing the reduction in a percentage going from E0 to simply adding ethanol to make E30. So we have a percentage reduction for 3 vehicles. The top chart is mass, because that's how we regulate PM, or will in the U.S., but the Europe and other countries are adopting a number. So there's always a mass or a number to discuss. But the reduction here is always consistent, while there is variations because it's a difficult measurement to take. We were seeing that simply adding ethanol made significant reductions. The blue bar is a city driving, and the gray bars are a heavy highway driving. And that, again, is just the reduction of simply adding 30% ethanol with these 2 fuels.
Steve?
Yes.
I think it bears explaining a comment you made earlier, which is that we measure particulates by mass or number. Not everybody could be familiar with that.
Okay.
Mass, of course, means weight, so you just weigh the particulate matter. But if the problem area starts to become these tiny ultrafine particulates, they don't weigh much, but the number of particles in the brew is going up, and that's exactly what's happening with the newer engines.
Right. The number's going up. Also, as you have a higher number, you're going to have, with the same mass, you're going to have more surface area. And that's where you're finding, because the pHs is what creates the UFPs, you're finding the pHs will coat the UFPs. And so in Europe, they felt it was better to regulate the number, because these smaller ones, these sub 23 nanometers, and we're talking PM.01, not PM.25, that is what's more toxic to get into the bloodstream. And so that's why in almost all these automotive studies, they will give you both the mass by weight and the number per mile is typically how they do that. But again, this is the percentage reduction for simply adding 30% ethanol. Another study we recently did is we asked the North Carolina State University to test 5 vehicles using 3 consumer fuels, but also a E25 by simply adding ethanol to that E10 regular. And in that, we were statistically lower, not only on the PM, which you see here, and the CO, but we were also better on efficiency. So we had the greatest CO2 reduction because of higher octane when we were comparing the E25 to the E10 regular. And also to mention that 4 of the 5 vehicles here are non-flex, and as we monitor the computers, these vehicles did very well adapting to the higher blends. And so this was a very interesting study for us using PEMS. We were on-road testing using portable emissions system testing, which is becoming very popular because there's a growing concern that the certification data or lab data isn't measuring real world. So here we have a nice reduction as we compare the first fuel to the second fuel for PM/CO, and there's other information in that study as well on CO2 emissions. So we really didn't have any emission or mileage reduction with E25. More recently also, but a series of 3 studies with the University of California, Riverside. We asked them to test 2 FFEs, and so you see in each category 2 FFEs, number 1 and number 2. We created a high and low aromatic. Now this is the SOA data, the PM going into the SOA. I'm just showing the SOAs here, or the PM. The SOAs is also very similar to this, but when we compared the high and low aromatics, the SOAs went up, the toxics went up, and then when we simply added ethanol, again from the E10 to the E30, we saw a very nice reduction with comparing E10 to E30 in both vehicles. So aromatics was increasing the PM and SOAs, and the ethanol was decreasing. I have 2 studies here because I think it's almost really important to have these 2 together. Is part of our work was, or UCR was sending these PM samples to the University of Wisconsin for toxicity testing. And so we found that the toxicity was pretty much related to the PM mass. If we could reduce the mass per mile, we were reducing the toxicity of exposure. But the study also didn't find a lot of mutagenic emissions with our PM samples coming from the tailpipe. The second study here is by EPA directly, where they were looking at the mutagenic emissions from what happens with aromatics after the tailpipe, the first 24, 48 hours. And I think this is really important because this is EPA saying that although we regulate the tailpipe VOCs, we're doing nothing to regulate pretty much the products of photooxidation, the SOAs. And that the mutagenic creation of this stuff was directly related to the photooxidation. And that lastly, most of these aromatics in urban areas are man-made, so we're not talking something from vegetation or something like that. So changing a little bit here, what is the biggest challenge to creating a better fuel? What is the biggest challenge in promoting higher blends of ethanol to reduce those emissions? It is our view that it's the test fuels. Whoever creates the test fuels is controlling the outcome of the study. There is no standard today in how test fuels are blended. So there's a lot of conflicting science out there that people are relying on to make policies, but you really need to go back to how were the test fuels blended. So there's a lack of consistency in our science in this area, but as I said earlier, when we simply add ethanol, we make it better. And that comes back down to this two ways that's going on today with test fuels. This match blending allows the test fuel providers to do pretty much anything they want. You can change a lot of things in fuel to hold the few parameters constant. But in the term of splash blending, again, simply adding ethanol, ethanol has a very favorable story. So as we brought our information to the autos, Ford and General Motors actually published this paper in 2014 into regards of how EPA was allowing their test fuels to be blended. And these two key statements are right in the abstract that the exclusive use of this match blending is fundamentally flawed. And secondly, a lot of these emission increases EPA and others say are occurring because of ethanol are due to the added aromatics, but unfortunately being incorrectly attributed towards ethanol. So work we're doing in this area is a little over 2 years ago, we started with an outside consulting group of a very reputable oil refinery consultant and some gentlemen retired from University of West Virginia. And we did a meta-analysis where we went back to all these studies, and we not only looked at how they modeled the emissions, but we looked at how they blended the test fuels. And we saw a pretty interesting trend there that a lot of these match blended studies are not matching real world, and they can be very negative for ethanol in certain areas. But that's not the truth. That's not fact. I mean, we can compare, again, greater aromatic reductions in the real world. So with that, we did this meta-analysis that's found online. We published a secondary, another paper, Society of Automotive Engineering paper last year. We also have another paper coming out using real-world fuels in EPA's model. That has been accepted and will be published here in a few weeks. And lastly, we're working with a wide group of stakeholders to include oil refineries, the autos, CARB is on there, test fuel providers. We're actually trying to develop a fuel blending guide, something that we can inform these researchers who are doing the modeling that are not fuel experts, but they're modeling the results of this study and not having the information there of what they should be modeling. In our past, we found studies that accidentally modeled the wrong fuel, or we found studies that weren't very truthful in their blending because we understand how these properties should change. So with that, reducing aromatics is simple. We can be putting limitations on that. Ethanol is readily available. It will reduce the toxic emissions and increase octane, protect public health. And I believe if it was done correctly, we could be looking at a greater than 50% reduction, maybe 70%, especially in urban areas in the summertime when this photooxidation is more important. So with that, I thank you for your time.
Thank you, Steve.